Yeah, as Jeff pointed out, I was an honours student of Ross's a couple of years ago, and we did some work on trying to see if we can develop a minimum model to try and explain some of the behaviour that you see in enzymes that have been implicated to harness hydrogen tunneling to enhance the catalytic rates. So, briefly, I'm just going to describe some of the necessary background that needs to be understood, look at some of the experimental evidence that there is that hydrogen tunneling might be occurring in certain enzymes. I'll then go on to talk about the mental model that we developed to try and explain what's going on here, to try and capture some of the essential physics that might possibly shed some light into what's going on. And then I'm going to talk about some of the results that we were able to achieve. So, hydrogen tunneling in enzymes remains controversial. About 2 years ago, there was a meeting at the Royal Society where they had a number of the people from the community that work in this area, the experimentalists, the theorists, trying to present all the arguments and get some discussion happening. I've taken some quotes from a couple of papers that have been published recently, just to show how differing the views in the community are. So there's people in the experimental camp who believe that you need to invoke both quantum mechanics and enzyme dynamics to explain some of these the kinetic anomalies, whereas there's others in the community who believe that all that's happening is that you have the enzyme simply stabilizes the transition state and there is no influence of the dynamics, and the quantum mechanics is kind of trivial. So there's a broad range of opinions in the community as to what's actually going on. So, not everyone here knows what an enzyme is, so I'll quickly run through. So, essentially, an enzyme is a large protein that catalyzes a biologically relevant chemical reaction. So, all it does, it speeds it up without being actually used up in the particular chemical reaction. They do this by stabilizing the transition state. So, typically, this is some kind of electrostatic effect in the. So, you have your reactants and your products, and the state that's in between the transition state. There's some kind of there might be a charged, it might be an unstable charged state, and there might be some kind of residue there that stabilizes this charged state. So it reduces the energy of activation, so that increases the rate of reaction. So hydrogen transfer reactions are very, very common in living organisms. In fact, they're one of the most common reactions. And so it involves breaking an XH bonds where X is either a carbon, nitrogen, oxygen, or could possibly be a sulfur. And one of the standard techniques to characterising these kind of reactions, especially to determine kind of the kinetic, so how which particular hydrogens are involved in a reaction, you do an isotope substitution. So with hydrogen, you've got deuterium and tritium that are available for you to go and have a look at what goes on. So you go and you change the hydrogen that you think is being transferred to one of your isotopes, and you have a look at how the kinetic is altered. And typically what you see is that the rate of reaction slows down. And you can explain this relatively straightforwardly using a semi-classical idea. So the rate at which a reaction proceeds, how it depends on temperature, can be described by, to a large extent, kind of using a Boltzmann factor argument. So you've got this, that the rate is proportional to some pre-factor times the exponential of the activation energy divided by the ambient thermal energy, kVt. So the rate at which the reaction proceeds depends strongly on how large the activation energy is relative to your ambient thermal energy. And so if you look at a carbon-hydrogen bond state, you can look at the ground state of that hydrogen, that bond as a quantum harmonic oscillator. And so if you kind of have this classical picture of the potential surface, but the actual energy of the CH bond will not be right down the bottom. There's some zero point energy associated with that, and that depends on the actual the frequency of vibration of the actual bond. And so if you go and you make the hydrogen, change the hydrogen to a deuterium or a tritium, what you're doing is you're reducing the actual frequency of vibration, and you're actually deepening the 0 point energy. So what happens is there's a larger effective barrier that needs to be overcome, and this is why the reaction slows down. Okay, so this is perfectly well understood. It has been since probably the 50s people have looked at this. Okay, but the problem is in these systems where hydrogen tunneling has been implicated, you have kinetics that goes beyond this description. So what typically happens if you have a semi-classical, if you use a semi-classical framework, what happens is if you look at the ratio of the prefactors, the Arrhenius prefactors, if you determine with different isotopes, that they're roughly equal to 1. Okay, there's a slight deviation, but in these systems you see large deviations away from this. So you get two general classes. There's strong temperature dependent kinetics, isotope effects, and weak temperature dependent isotope effects. So in strong temperature dependence, you have the ratio, if you look at the pre-reactor, for the light isotope to the heavier isotope is much, much less than 1. And you also get that the difference in the activation energies is actually much larger than what you'd expect if you use this kind of straightforward, the semi-classical idea where it's just the difference in the 0-point energies. So there's the other class is kind of these systems where you've got this weak temperature dependence, where the prefactors are typically very, very large, and that the activation energy is less than you would expect using this 0-point energy algorithm. So when you're trying to think about these kind of problems, it's important to keep in mind what the important energy scales are and how big different things are relative to each other. So if you look at 300 Kelvin, it's about 2.5 kilojoules per mole. The actual the energy spacing between, if you have just look at a carbon-hydrogen bond, assume it's a simple harmonic oscillator, you get an energy spacing between the states of about 36 kilojoules per mole. With some of these systems, quantum chemistry has been done to go and evaluate how sharply curved the barrier is. So that's just the inverted parabolic potential that separates the reactants and product states, and it comes out to be around 10 kilojoules per mole. The actual activation energy for these kind of reactions varies by quite a substantial amount. So you get, with some of these reactions, you have the activation energy, if you calculate it using a straightforward Arrhenius plot, it varies from about 8 to about 60 kilojoules per mole, and it'll turn out to be highly relevant later on. And yeah, if you look at the difference in the activation energy between the tritium isotope and the hydrogen isotope, you get about 8 kilojoules per mole. So a system in which this is particularly apparent, this large kinetic isotope effect is soybean oxidase. It has a ratio, if you look at the rate of reaction when you've got hydrogen or deuterium in there, the hydrogen actually reacts about 80 times faster than the deuterium. And so if you use the semi-classical theory, it only predicts that you have a maximum of about 10 times. So this is one of the celebrated examples where people say hydrogen tunneling must be occurring. So what we did is we approached this trying to develop a minimal model that would capture most of the essential physics. So the role of the minimal model is to give some insight into what's going on, what you absolutely need to include in order to capture some of what's going on with this particular system. So in the model that we used, we made some assumptions about restricting dimensionality and treating the coupling to the environment reasonably generally. And so what we did is we turned to the Caldera-Leggett Hamiltonian, which essentially, so all this Hamiltonian does, you have your proton, or hydrogen, which you're describing. You've got the two terms that describe the motion of this particular particle and some potential, but then you have this other term, the coupling term, which allows you to couple it to some arbitrary environment. And so this is a highly analogous Hamiltonian to what Joel was talking about in the spin boson model. This is kind of a continuum version of that, and you can capture the influence of the environment on the system using a single function, which is known as the friction kernel, which is mathematically equivalent to the spectral density that Joel was talking about during his talk. So when you go from this Hamiltonian to a rank expression, what you find is that, so this work, this is a widely studied Hamiltonian, and a lot of people have worked on this, including people like Peter Volness, and there's a number of people who have worked on it in the last couple of decades. And what you find is that the kinetics qualitatively change in different temperature regimes. So what happens is there's this one temperature scale, this crossover temperature, that kind of dictates what happens in the system. So if you're in a temperature regime where you're far above this particular crossover temperature, the dynamics are essentially classical. You can describe the kinetics using the standard semi-classical behaviour, and you get your Arrhenius prefactor, and everything's very standard. But as you reduce the temperature and you get close to this crossover temperature, what happens is the rate expression gets modified, and you get these quantum corrections that modify the rate expression. So this is kind of where the dynamics, it's mostly classical, but there are certain quantum parts that are enhancing the rate of reaction. Then when you get way below the crossover temperature, one of the few ways to escape from the reactant or product state is actually through tunneling. And so this crossover temperature depends strongly on the coupling to the environment, and also, more so actually, on how curved the barrier is. So if you have a strongly curved barrier, you find that this crossover temperature is quite high, as you would expect. So in the low temperature regime, what actually happens is when you do the analysis, you have to do an imaginary time integral. Well, you have to look at what's going on in imaginary time, and you can describe the tunneling through the barrier using a solid solution. And what happens is below T0 you have the solid solution, so you have this kind of standard tunneling through the barrier. But as soon as you go above T0, the solid solution disappears. Okay, but you still have these quantum corrections above T0, and these have been attributed to tunneling from thermally excited states. So if you remember the barrier that I had before, so if you get a thermally excited state close to the top of the barrier, then you can have tunneling from those states. And a number of people have pointed that out. So what can this model explain? So what we've done is we've tried to take into account some of the kinetic isotope effect data that people have seen. The nice thing with kinetic isotope effect is that because you take the ratio of the rate constants for different isotopes, a lot of things cancel. And so the rate expression, well, the expression that you have for the kinetic isotope effect depends on a reasonably few parameters. So in the weak friction limit, what happens is that it only depends on the curvature of the reactant state and also the curvature of the transition state. And using, this is a particular data from a reaction that's analogous to something that happens in methyl elements of CoA mutate. It's the same reaction, but it's just being performed by different non-enzymatic catalysts. But the kinetics is still anomalous in the same way that the kinetics is for the particular enzyme. And what we found, this is a carbon-hydrogen, this is a reaction which breaks the carbon-hydrogen bond. The actual ground state energy, the ground state vibrational frequency is actually very, very close to what you would expect. And this curvature of the barrier actually gives you a crossover temperature that's about -10, -20 degrees Celsius. So at physiological temperatures, you're not going to be seeing the instanton solution, and the only thing that's going to happen is you're going to have this kind of tunneling correction from these thermally excited states. So we did that with that system. And there was another bunch of data that was published for bovine amine oxidase, where again tunneling was attributed, and using the same kind of analysis we could determine the curvature and the reactant state was about 2,100 wave numbers, and the barrier was again close to about 1,000. With this particular system, people have done some quantum chemistry and they've actually gone and calculated the barrier, and it came out to be very close to 1,000 centimetres. This 2,100 is substantially lower than you would expect for typical carbon-hydrogen stretch. Not quite sure why that is. There could be some relaxation in the bond, but the fact that this was the same order of magnitude actually surprised me quite substantially. So what can this model explain and what can't it explain? So these two examples that I've spoken about before have fallen in the first class, where you have this strongly temperature-dependent kinetic isotope effect. So this is where the prefactors are much less than 1, and you've got this apparent activation energy, difference in the activation energy, which is larger than what you'd expect from this kind of semi-classical analysis. And so we've gone and actually derived expressions for using this the modified rate expression that's valid around above the crossover temperature. And you can actually take into account most of the experimental data that falls into this particular regime. However, this model cannot explain the cases where you have a weakly temperature-dependent kinetic isotope effect, where the prefactors are really, really large. Now, one thing that we've noticed is that the activation energy the hydrogen activation energy for these kind of reactions, the ones that we were able to explain, was reasonably large. So they fell towards the larger scale of that range of activation energies I showed you, from the 8 kilojoules per mole to 60 kilojoules per mole. These other systems, where it's got a weak cheap temperature-dependent kinetic isotope effect, fall within the regime where you've got a very weak, you've got a small energy of activation. And so one of the approximations that's made in obtaining the rate expression from the Hamiltonian is that you actually you have the restriction that your h bar omega naught needs to be much less than the actual barrier activation energy, and so that clearly breaks down in this case. There's also the possibility that you need to consider high dimensional effects, as Meredith pointed out and Jeff pointed out in a lot of these kind of cases. So the objective of this was to try and see what the minimal amount we could get away with to try and describe what's going on. So for these systems, that might be something that's important. Something that's also come out of a discussion we've had recently from the conference is actually looking at what the significance is of how large the actual ground state energy, the 0 point energy, is relative to the barrier. So when you've got a carbon-hydrogen stretch required, the 0 point energy is about 10, 15 kilojoules per mole. And when you've got an activation energy, it's of the order of 10, 15 kilojoules per mole. Okay, there's a lot of the rate of kinetics goes down, but the problem also is then your ground state energy is very close to being larger than the activation energy. And there's lots of strange things that can happen when you've got that going on. So yeah, we were able to explain some of the data, but there's other kinds of data that we were not able to explain. But there's a number of reasons why that might be the case. Okay. And I thank you for your attention.
Thank you, Jacques. Questions? Yep.
Can you explain to me why there's a maximum capacity of 10?
Oh, okay. So what you do there is you essentially assume you've got the kinds of bonds where you've got a large angular frequency. So for example, where you've got the strong bonds. So for example, an OH bond or something like that, where you've got a 4,000 wave number stretch frequency. You go and make the assumption you've got you look at the difference in the 0 point energies if you have hydrogen or if you have deuterium. And so you calculate then from that difference in activation energy, you put that in the rate law, and then that translates to a max of how much larger the rate should be for the hydrogen or for the deuterium.
So that would be for a single movement of a proton or a deuterium?
That's right, yeah.
So if in your protein you have 8 different movements, is it a sum of, or is it still sort of 10?
So if you've got, that's a good question. So if there are other shuffling processes that might be rate limiting, so that's possibly compounding, this could be relevant. And a lot of these cases, these systems are reasonably hard to find, and the reason people go to great lengths to show that it's only the single transfer of hydrogen that's actually the rate limiting step. So there's the experimentalists show that there's the single hydrogen shuffling is the only thing that's rate limiting.
Right, I understand. I mean, normally you look for a rate limiting step. You have a whole series of steps which are energetically more or less equivalent.
If there's a number of coordinated proton shuffling steps that need to occur, yeah. But I don't think that's the case in these kind of systems. I think you have to talk to an experimentalist to completely clarify that, but I'm not fairly certain that's not. Yeah?
Jacques, one of the sort of validations of the model is that you're predicting the isotope effect of the temperature dependence. I see we've got a very limited temperature scale level.
That's right. Yeah. So yeah. That's.
So what else can you tell me about the validation of the model versus other things that you've got a handle on?
Okay. So what the model can explain the observed the pre-factor ratios, and when you fit it, you can get these particular the numbers for the for the ground set frequency and the curvature of the barrier. And you're absolutely right, you've got a very limited temperature regime. But if you look at when you look at the theory as well, we can derive, I haven't gone through that here, but you can actually derive limits on the prefactor values and the activation energies, and all of the systems fall within that range, which is outside of the semi-classical. Right.
Yep. Quick question, following up from Paul. Is there any information, structural information you can get about the role of the enzyme in determining this? So is there some correlation between the enzyme structure
and the
barriers, the tunneling?
Right. Okay. So in this, what we've found, so in these systems, you're in the weak friction limit. So the coupling is not particularly strong, and so the thing that's kind of dictating what's happening is the profile of the potential energy surface, which you could argue is, the enzyme plays a large role in setting up that potential energy surface. But the question of how possibly dynamical effects coupling to the particular reaction by the enzyme might influence things, I don't think you can maintain it from there. You can obtain it from there. It doesn't seem to be insignificant in the systems in the class of systems we've been able to explain.
Just on that, but then, and I agree with what Jacques saying, but there are people who have a completely opposite view, which they very heavily push that the enzyme is designed to enhance the dynamics.
There's a huge debate in the field at the moment as to the ideas that people have shifted beyond looking at whether it is actually quantum tunneling to how protein dynamics can influence quantum tunneling. And so the dynamics that's been implicated in this has been large conformational changes in the protein. A lot of things have been kind of invoked to try and explain these large gating modes that might actually modulate the potential surface to increase the tunneling rate. But there's not really that much substantial evidence to back that theory up.
So, I'll follow out a bit, the different proteins, the different enzymes there that are you present. So what's actually determining that barrier? Say two different enzymes.
But is what's determining the size of the barrier, or so the size of the barrier inherent in a particular chemical reaction, and how effective the enzyme can stabilise the transition state. That's kind of
related to the structure then as well.
It's related to the structure, yes. The role of dynamics in that, though, is a bit open, I think. Any other questions?
I can wear the ICAM hat again.
Yeah, this conference has been really relevant. A lot of this, especially looking at why you have this weak temperature dependent, there's work that Meredith's actually done that is going to be highly relevant, and we're definitely going to pursue work together to try and see how relevant that might be to our system.
Yes, that's exactly what I was going to say, Meredith.
Yeah.
Expert on all that. Has a PhD on it. So, by combining the two aspects, there's a lot of chance for advancement, both what Meredith has been doing and what you've been doing. And incidentally, Meredith has a lot of comments to say about tunneling in proteins as well, too, and she's saying exactly the same thing as you are, from a completely different perspective.
Right, okay. Yeah, perhaps that's future work, yeah. Okay.
Yeah. Thanks, Jack.
What's happening? I think we should go for lunch, and then